So major tools in this. So that is what is ECO. It's a process is difficult. It's a time consuming process, and it depends on, there are lots of people who will review your ECO. Only then, once they feel that it is required for that chip, then only you'll get the approval to do the ECO. That's how the industry practices. And major tools in this formal verification are conformal LEC, logic equivalence check, and formality. So these are the company's cadence and synopsis. Now we'll go to the topic called as synthesis. So basically what a synthesize is converting the RTL into optimized netlist. So each synthesis process has three steps. Whichever tool you use, whichever vendor you use, these are the three steps which we have: generic synthesis, mapping stage, and incremental optimization. So I'll explain you what are the inputs needed, what are the outputs we get, what are the tools in the market are. So behavior description, that is the RTL, technology libraries. So this is where we define whether my design is 5 nanometer or 7 nanometer or a 4 nanometer. So each technology will have library. So what exactly the library contains? So what library contains is all the components which are needed in the design. So we might have learned that the basic components are like AND gate, NOR gate, NAND gate for the combo logic, and for the flops is D flip flop. So in the libraries, for each component, say NAND gate, so there will be two input NAND gates, three input, four input, five input, multiple input NAND gates. And each of them will have the properties, like what is the capacitance of this NAND gate, what is the resistance of the NAND gate, what is the delay of this NAND gate, what is the delay of everything. So in the technology libraries, those each component properties, they are defined. So why do we have to give so many? So for just two input NAND gate, there will be different uh, properties. So some might have less capacitance, some might have more capacitance, some might have less delay, some might have more delay. So you might ask why we need so many components. Why not one component for each two input NAND gate? So depending on where your NAND gate is being used, where you are in the design, so tool will choose based on that, depending on whether that path is a critical path or that path is, it's a normal path where we don't, tool doesn't have to work so much. So based on that, the tool will pick that specific library component. So we can specify that to the tool that no, always pick this kind of things, always pick that kind of thing. Will do. Then we have something called as design constraints and design environments. So design constraints is like we are specifying clocks, input delays, multi-cycle paths, or a false path. So output for this is optimized netlist for further processing, like wherein we do the backend and all those stuff. So what other tools in the market are Genus from Cadence, Design Compiler from Synopsys, or Formal Compiler. They have different names. They come with the different names altogether. So some of so so this is the things. If you have any questions, please write it to the team. We'll have a discussion at the end of this. So then we have, okay, now I'll explain what are the each components here. So behavior description, technology library. So these are standard in the market. So we cannot as I explained, what was this thing? This is a general article which you write. Libraries is whatever you have libraries, you use them. Design constraints and design environments. I'll just give a brief on what is design environment and what is design constraints. So design environments are comprised of processor parameters, IO attributes, design rule checks, wire load model selection. So what is wire load model? What is, so these are the things. So what is this library? So what kind of library? Slow library. So each component will have a different libraries. So we use those things based on that. Then left. So when we are running the tool. Okay, so as I said, right, floor planning we do. So in nowadays the tools have evolved so much that if you give the floor plan in beginning itself to the tool, based on that floor plan, it will do the synthesizing, it will do the optimization, it will do the connectivity and all those things, and it will, based on that, it will give us the numbers means how much is the, what is the power, what is the area consumption, what is the timing. So those kind of things based on that. Then you have capacity table file which we provide, QRC, that is resistance, capacitance, and all those things. Clock gating, true or false. We are, this is one of the conditions we say whether I want to have clock gating in my design or not. So basically, clock gating is something wherein it's used for low power designs, wherein if you want to restrict the clock supply when the module is not running. So that is what we do. So these are the things called as clock design environment settings. Then we will talk about synthesis design constraints. So what does design constraint mean is properties of the clock, the frequency, delay, duty cycle, skew. Timing exceptions in the design include multi-cycle path or a false path or maximum delays. What is a maximum delay in the things? Okay, so what is a multi-cycle path and what is a false path? So multi-cycle path is, say, from one point A to point B. Say for example, you are implementing a multiplication in the design. So, and we know that multiplication might not happen in one clock, but generally for a tool, every point A to point B which has a flop. So basically for a tool, point A to point B is from one clock, from one synchronous module to the another synchronous module. So from a flop to flop, that point is called as a, that is one path for it. So if you're implementing a multiplier or some logic, you have a combo logic which is huge combo logic, and you know for sure that in the design you will not be able to send the data from one flop to the another flop in one clock. So you define that it will take more than more than one clock or two clocks or three clocks depending on your design. You can mention it as a multi-cycle path. False path is something wherein, say, you have clock 1 and clock 2. So clock 1 and clock 2 do not cross each other. Any signal from clock 1 to clock 2 do not go. So then you have to specify that, or they might go, but you don't want to constrain it, or you don't want the tool to spend time on it. That's what you define as a false path. I'll give an example of how a constraint file looks like. So here we are defining the clock. So create clock, you can give any name you want. Then you're adding the period. Then you're saying that it is a square wave, or you want to have 50-50 duty cycle, or you want to have different 25-75, depending on your design, you can specify. So in the waveform, if you're putting half of this, it is a 50% duty cycle. If you want to change, you can change it. Then you're saying get the ports clock. You are asking the tool whenever, wherever there is a port CLK, you're naming it as CLK. You can give it some other name based on your design, whatever you want to do. Similarly, for another clock which is at a different frequency, so you give this period. Then all the ports, right? So input ports will have certain delays. Why we need delay in an input port is in an so on an SoC or on a chip, any chip, not just SoC, on an ASIC or any of the chip, right? So when the signal comes at the input, there will be a certain delay after which basically it stabilizes and comes to your module. So this delay is f- for the signal to reach your module from the start point. So which port has how much delay? There might be ports which are different delays. Which clock is it associated with? So we are saying that it will be associated with this clock as we have defined here CLK. So this clock, and this is the delay which will be there for inputs. Then we do the for that port. So this is a sample of how a constraint file looks like. Now we'll look at what are the steps in synthesis and why, what what each step does actually. So generic. So as I said in the beginning, right, we have three stages. One is generic, mapping, then incremental optimization. So what happens in generic synthesis? So in this step, tool replaces the code into generic cells. These are technology independent cells. So say for example, you are writing code saying that you're doing a full adder. Okay. So we know that full adder contains so many AND gates, so many OR gates and all those things, right? So in the generic step, what the tool does is it just replaces the whole full adder. You just write a single step in a equal to say z equal to a plus b plus c. So when we write a plus b plus c, the tool will understand that it has to do some operations. So it will directly convert into what is a plus b plus c in the generic, say AND gate or an OR gate or anything. Simple. It will not depend on. So as I said in the beginning, right? So it can choose any of the AND gate. So it will not choose any of the AND gate. It will just replace a plus b plus c with a and b and c and d, all those steps, whatever. It will expand the design completely and replace them here. So in the mapping stage, what it does is, so whatever generic cells which have come, right, will be replaced with the technology library components based on our requirement. I'll just show you what kind of requirement. We might say that generic effort medium components don't put in much efforts. Map optimization step, we are asking the tool to do high. High means it will replace with the best components. Okay, so say for example, so that is what happens in the mapping stage. So it will replace based on the effort which we have given, right? So it will pick the best components. If we give high, medium, low, so low means it will not, the tool will not spend much time in this stage, mapping stage. So tool will just do replace any component which it finds and adds and does that. Area and any other parameters as per settings. So say in the design you want to constrain based, you have a timing as your constraint. I don't mind the power or area. So what the tool does is it works on timing. It will not work so much on power and area. Say if you have a power constraint, so you say the tool that okay, I want to optimize based on the power. So how do you define the timing power area is based on the libraries which we select. So it will automatically synthesize and optimize based on those things. So optimized based on which are provided. So that is what I have explained here. So so what we do is once we give all the parameters, the design constraints, design environment. Once uh, we give the RTL, we give the technology library. Once we set the conditions, we do is a step called as elaborate design. So what the elaborate design is, so it starts with the generic stage first. So once it does the generic stage, it will check the design. Check the design means whatever linting checks we do, right? So synthesis also does the same thing, because synthesizing, we don't, synthesizing tool will also do its own checks whether if there are LHS and RHS are matching, or there's a latch in the design whether you intended or not. So it will list out everything for us to review it. Check design, check design unresolved. So it will list out every component which is not matching with the required spec. Then it will do the generic synthesis, mapping stage, then incremental optimization. So at each stage, it will generate a netlist for us to compare, to check from mapping. So depending on how you want, you can take the output after mapping, or you can take output after incremental optimization. So outputs of this step, basically synthesis, are a netlist and an SDC. So some constraints which tool also applies on its own, it will generate a report of the constraint. So whatever SDC or a constraint file which give as an input, right? So those constraints which are getting applied, and some other constraints which tool generates based on the parameters which we have provided, it generates the output also. So this finishes the major implementation side of the uh, front end. Now I'll just give what kind of opportunities are there, what kind of market is there for this. So generally a lot of services industries look for people with background or have a knowledge on lint and cdc, because see how it is when you are a fresher and when you enter the market, it is difficult to get into product company. Some get, some don't get. So once, so fortunately or unfortunately you get into services industry. So when you go to your the client companies or product companies, they will put us on to work on linting and cdc. So they, because as design is evolving a lot and there will be multiple revisions of designs and there are multiple chips which are working, so we'll have continuous work on linting and cdc. So what we do is they'll be changing some parameters, they'll be changing some clocks. So from our end we have to run the lint tool, cdc tools. We have to generate the reports, we have to see if all the reports are correct or not. If we need to fix anything, we don't fix as is, we check with the seniors whether that is the right thing or not. Review and synthesize. Once you go into a product company, you still do the linton cdc, but not that much. We will, if we are lucky enough, we get to work on synthesize and some of the sta is standard timing and static timing analysis. So here we compare basically we do is set up and hold checks in the design, whether there are any timing violations in the design. One other thing I forgot to mention is in synthesis, we fix all the setup violations. Setup violations is when the clock, the data should be stable before the clock edge occurs. So in the backend, we fix most of the hold violations. That is, stable should be signal should be stable even after the clock trigger happens. So this is basically how our timing is checked, whether setup and hold. So if these two meet in the design, then your your design is timing safe. Okay. So what are the companies and how the roles are? So generally as an entry level, we join as a design engineer or an associate engineer or an engineer. So if you're joining an IP team, we will be given mostly the linting and CDC and RTL work, but it will not be major. So it's like, say, for example, you join a company wherein they make multiple chips, right? So they'll be depending on the application. So same chip is used for different applications. So depending on the application, some features might be removed, some features might be added. There'll be a standard design which is already there. You have to sometimes you have to comment some things, you have to add few things. So what we'll do is we'll make those minor changes and we'll do our linting and CDC checks. On the integration team, if you're joining the integration team, you'll be doing both. You'll be doing synthesis basic level. We won't be running. There'll be a proper full-fledged team which will do the complete synthesis. As an entry-level engineer, you just run these things to see if flow-wise you're clean or not. Then you can pass it to the synthesis team, which will do the whole synthesis step. So some of the companies are Intel, Qualcomm, AMD, Broadcom, TI, few of the product companies, then Altran, UST Global, Insemi, Wipro, TCS, L&T are some of the services companies. So that's it for the presentation.